In this video, we'll talk about the other kind of transistor, which is a MOSFET transistor, or a FET. So, FET stands for Field Effect Transistor. And it was, field effect transistor. And it was invented before the bipolar junction transistor, but the technology didn't exist until after BJT transistors were actually made. So FETs were made more recently, but they were invented earlier, in theory. Here's a drawing of what a field effect transistor might look like. Just like for the BJT, the field effect transistor is a 3-terminal device. They have different names, just to confuse you. Different names from the bipolar junction transistor. So for a field effect transistor, the 3 terminals are gate, source, and drain. And again, we have P-type and N-type materials. And just like with the BJT, where you could have either PNP or NPN, where the charge carrier were holes or electrons, with a field effect transistor you can also have P channel or N channel. The most common type of field effect transistor is a MOSFET, and that's metal oxide field effect transistor. And for a P-type MOSFET, look like this. So we'd have 3 different materials. We'd have N, P, N. So this is P-type MOSFET. And then the metal oxide comes into play on the gate. So let me see if this other figure will show it better. Well, except this is the wrong kind of MOSFET. But anyway, just look at this part. So here is the metal for the gate, and then here is a layer of silicon oxide. And this is an insulating layer. And so that separates the gate from the body of the transistor, whereas the source and drain are connected directly to the transistor. So this oxide layer separates the gate. So we've got that oxide layer here separating this terminal from the transistor. And the way this P-type MOSFET works, shown here, this is depletion mode. So what that means is when we have 0 volts applied to the gate, then we have this conducting channel. And then whenever we apply a voltage to the gate, if we have positive voltage here, then well, actually we would control this with a negative voltage, excuse me. So we supply a negative voltage to the gate, and that would increase the size of these N regions. So that's supposed to be a drawing showing where the N regions are getting smaller, and so this conducting channel is getting pinched off. The N regions are getting bigger and pinching off the conducting channel. Okay, so as we apply our signal, we are depleting the conducting channel, and so the resistance of this transistor increases. And so in order to turn it off or to close the switch, Okay. That might not have been clear, but we'll go over it again. So here is another type, which is the N-type MOSFET. And rather than make a drawing, let's just look at this figure. Okay, so here we have N-type substrate, P-type, and an N-type substrate. And there is a region in between the two N-types of P-type. And so as it currently exists, there's no way for electricity to conduct between the source and the drain. And again, source is the source of electrons. So electrons are the charge carrier for this N-type MOSFET. And so source is connected to ground. And then the electrons go to the drain whenever current's flowing. So you might think of source, you might want to connect that to positive and drain to negative because of current flowing, but it's really the opposite because the charge carrier is electrons. So source is ground and drain is where we apply VDS, the voltage difference between the drain and the source. Okay, so currently there's no conduction possible between the drain and the source. And this is an enhancement mode MOSFET. So that means as we supply or apply our control signal to the gate, then we introduce a conducting band. So here's a figure showing the cross section of the MOSFET and two regions or two states that this transistor can operate in. So first we have cutoff, and that's whenever our gate voltage is less than the threshold voltage. So again, we have no conduction possible between the drain and the source. But then as the gate voltage increases, so here we're applying a positive voltage to the gate, then electrons are attracted towards this region and we create a conduction layer. And so now we have conducting possible through these free electrons here in the N-type, and then these electrons that have been attracted by the positive voltage on the gate. So we apply this positive voltage to the gate, and once it gets above the threshold value, then conduction is possible between the drain and the source. And as we increase the voltage on the gate, more electrons will be attracted, and so we'll have a wider conduction layer, and so more current can be conducted between the drain and the source. So the BJT was a current controlled device. The amount of current we supplied to the base changed the amount of current through the collector, and here with a field effect transistor, it's a voltage controlled device. The voltage that we supply to the gate affects the current that goes through the drain, so ID. And one thing that's nice about that is that this resistance is virtually infinite, and so no current is taken, so we don't lose power whenever we're using a field effect transistor. So if we're controlling this, whatever device we're using to control this transistor isn't putting any current into it, so we're not losing power. And this figure shows the other two operations for the MOSFET, the linear and the saturation regions. So in both of these, the gate threshold is above the gate voltage is above the threshold voltage. So we're in these figures, we're going to keep that voltage, the gate voltage, constant, and we'll see what happens as the drain to source voltage increases. So for small drain to source voltages, this just acts like a resistor with a very low resistance value. And so as the drain voltage increases, the drain current increases also. So there's a linear relationship in that region. So it's called the linear region. Then, as the drain voltage increases, what's going to happen is that the difference here between the gate and the drain, so on this end of the MOSFET, that voltage is going to decrease. And so there will be less of a pull for the electrons that are creating this conduction channel. And so it's going to increase the resistance of the MOSFET. So as the drain voltage increases, we get less increase in drain current because now we're increasing the resistance, so it's becoming less effective as a conductor. And that continues all the way to the point where the difference between the gate voltage and the drain voltage is the threshold voltage. So now we are at the point where there are no more free electrons right here. And so after this point, the relationship between the drain voltage and the drain current becomes flat. So from here on, increasing drain voltage doesn't increase the drain current like it does in the linear region, because an increasing drain voltage is going to push those electrons. We'll actually have a negative voltage between the gate and the drain. And so the electrons are pushed away from here, and so the conducting band is smaller. But it still conducts electricity because that's offset by the potential. So electrons still do make it through from the source to the drain. But so what we have here is that the drain voltage increase doesn't change the drain current. So that would be the saturation region. And here's a figure from a MOSFET that we have in the lab, and this shows the drain to source voltage versus the drain current for different values of the gate voltage. So you can see here if the gate voltage is 4 volts, as the drain current increases, we start to enter the saturation region, where changes in drain voltage don't affect the drain current. And that happens about at a difference between gate and drain of around 1 volt, a little less than 1 volt. So here you can see that the transistor is acting like a resistor, a really low resistance value. So it's maybe 1/10 of an ohm. And then here, changes in voltage give you no change in drain current. And so that would be acting like a really large resistor. Whenever we want to use the MOSFET as a switch, or at least the N-type MOSFET, what we would do is we would do low side switching. So here's our load, and there's our voltage source. So there's a symbol for an N-type MOSFET. And our control voltage, VGS. So whenever we're using the MOSFET like this, we want the transistor to stay in the linear region where we can conduct as much electricity as possible. So that linear region is here. And so that N-type MOSFET, we have the source connected directly to ground and then the load above that. And so this is referred to as low side switching. And so for an N-type MOSFET, this is the configuration that one would use. So now this voltage the voltage between the drain to source is going to be small because most of our voltage drop will be across our load. And so with that small voltage from the drain to the source, we'll be sure to operate here in the linear region. So that's the introduction to the two type of transistors, and we'll look more at some examples of implementing them, and then we'll also use them in applications.